All right, remember you should have your notebooks and your Chromebooks out and ready to go. Probably get off the Minecraft. Oh, I don't know. I probably don't need to look to know. Okay. All right, good. All right, let me take attendance real quick. Good, good. Yep. Uh-huh. Yep. Totally. Not. Nope, that one's not. Oh, and then you have relocated. You don't want to be alone. Nobody wants to be alone, man. Well, sometimes, right? Sometimes it's okay to like be alone for a minute. All right. Go ahead and open up 1.4. Now, some of you, correct me if I'm wrong, extra conversations need to stop. Correct me if I'm wrong, some of you probably did some of the reading. I don't think anybody did all of the reading. Is that true? You did? Okay. All right. How about this? How many of you finished the 10 questions, the actual practice? Got one? Okay, fair. All right, so what I'm going to do is we're going to go through this lesson as fast as we can with the caveat that if I'm going too fast, you say, slow down. Maybe just go, whoa. Okay, so here we go. Where's my mouse? There it is. And it is a long lesson, guys, so I don't mind trying to go fast through it, but if there's a point where we need to double tap something, please, let's do that. All right, we got a picture of a giant computer. You guys see it? Giant computer here. And this is a picture from, I guess, 1949. And it's in Australia. And this is a digital computer that takes up a very large room. Do you see the screen? No. You don't see the screen? It's a digital computer, so it should have a screen, right? No. No? Where's the screen? Did they have screens in 1949? No. Sure. Sure. Like old school TV screens, like cathode ray tubes. They didn't use that for this. Okay? This is your screen. This is a screen. What are they? Can you see the picture? Receipt printers? Okay, yeah, they kind of look like receipt printers. They are printers. There's rolls of paper, and so you'd input the whatever program you wanted it to execute, and it would print. Instead of having a screen, it would print on paper. Okay, cool. And then the paragraph goes on to say that, hey, a modern laptop has more computing power, and now we're even further along than when this was written. So much, my smartphone probably has like 10 rooms of computers like that, at least. Cool. What is the place of mathematics in physics? It's to quantify everything. Can you make observations? We've gone over this in science without putting quantities on it. Yes, no? We would call those qualitative observations, right? But if you want to put some measurements in, now we've got numbers. Once we have numbers, we can do math. So we can actually look at observations, take measurements, and do some math, and look at mathematical relationships between different things. Math is everywhere in physics, but we can do some conceptual physics, understanding this happens and then that happens without very complicated math. Scientific notation. Your I can statement for today says, I can make sense of very large or very small numbers with the scientific notation. So by compressing ridiculous numbers like this, the mass of a lead atom is lots of zeros, 3-4 grams. We can convert that to scientific notation. So let's do that real quick because it's down here. Let me scroll up if I can. No, don't look. There we go. So what would this number be in scientific notation? Does anybody know? Did you guys get that far? Okay, so what you do, if I have 0.0, a bunch of zeros, 3, 4 grams, I'm going to put the decimal in between, not in between, I'm going to put it after the first non-zero digit. So the first non-zero digit would be 3. So then I put the point here, and then the 4. All of the zeros that came before that are not significant, and we'll talk about significant figures later. But that would be it, times, have you guys ever seen this before? Times 10 to the something? Good, good. So you guys have done this before, but maybe a little rusty? Okay. This is the easy part, no. Because you lose track of your spot. So count with me. If you've got your computer open, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 places, and we're going to the right. Okay, so here's another rule for you to write down. If we're converting a really big or a really small number to scientific notation, if you have to move the number to the left to put it into scientific notation, it's going to be positive. If you have to move it to the right, it's going to be negative. Got it? If you don't have that up here, it should be where? In your notes down there. Good. All right. So we also have this really, really, really big number. So we did a small number making it scientific notation. Now let's do this one. So 25, good grief. I don't even know what that is. We're past trillion. So I don't know past trillion. What is it? What's the next one? Is it quad? Okay, I believe you. So we have thousands, hundreds of thousands. We've got millions, billions, trillions. Then you said it's what? Quadrillion. And then what's after that? Oh, you guys are better than I. Okay. All right. So we're going to take that. What would the numbers be for scientific notation? 2.5, because 2 is the first non-digit zero. So we're going to go 2.5. Are any of those zeros significant? No. And if you don't know that yet, there's rules for that too. We'll get to it. Now, if I put a decimal right there, the rules say all those would be significant. Ooh. But fortunately, there's no decimal there. So 2.5 times 10 to the what? Go ahead and count those up. You count on your own. I'll count over here. What'd you get? Now that you were waiting for me to do it. Good grief. I got 19. Yes? Yes? Hello? No answer. I counted 19. Was I wrong? I make mistakes. Could we do it easier than counting every single one? 1, 2, 3 at a time, right? 3, 6, 9, 12, 15. Whoops, did I miss one? 1, 2, 3, 4, 5, 6. 6 times 3 is? 18. Okay, hold on. What did I say, 18? Plus 1? So 19. Didn't I say 19? I was right. All right, so 19, is that going to be positive or negative? Positive, because we went to the left. Good. All right. Wait, is that done? What did I forget? The what about the measurement? The unit. What was it again? Kilometer? And then that one was in grams. Can't forget those. Don't forget the units. Okay. Let's keep going. So the whole idea is to make big and small numbers more manageable. Okay, believe it or not, how many of y'all look at this and say, I'd rather deal with the one that doesn't have all the gobbledygook, right? If you thought this looks more complicated, I'd rather just do the lots of numbers. Trust me, once you know how to do it, it will be easier, okay? Significant figures. All significant figures are maintained when putting things into scientific notation. The zeros that were over there weren't significant. The zeros that were over here weren't significant. That's why we got rid of them. But we kept everything else. All right, here we go. Express. Now we'll do this one. express this number in scientific notation. Never mind, we just did one like that. Why would we need to do another one? Are we good? You guys want to do that one? We can. Like I said, we'll go as fast or as slow as you need. And this one working in reverse. So if we have, we're going to work in reverse now. So we put it into scientific notation. This one is asking us to take it out of scientific notation. So 8.43 times 10 to the 5 is going to be what? If we take it out. To put it in, it's got a positive number, which means we had moved the decimal place which way? To the left, which means to take it out, we're going to have to move it to the right. How many places? 5. So we'd have 1, 2, 3, 4, 5, right? So it'd be 8, 4, 3, 0, 0, 0. So 843,000. They don't have a unit there. So whatever the unit is. Any questions on that? Reversing the scientific notation. Operations. Adding, subtracting, multiplying, and dividing. There are specific rules. Make sure you put these rules in your notebook or have them very well ingrained in your head. It's up to you to decide which is appropriate for you. If you are adding, let me highlight where it talks about it. If you are adding or subtracting, the exponents must be the same. To add or subtract. If you have numbers in scientific notation like this, if you want to add or subtract them, they have to have the same exponent. If they are not the same exponent, can you add or subtract them? No, you would have to do what first? I mean, I guess you could completely take them out of scientific notation, but the whole point is to make it easier to put it in. So we would just convert to make them the same. We would make the sign. And look, if we had like 10 to the 5th, something something times 10 to the 5th, and something something times 10 to the 4th, wouldn't we just have to adjust one of the numbers by 1 decimal point to make them the same? Yeah. Okay, and we'll see that in one of these examples here, okay? So we got to adjust it. And then we can go ahead, and what you do is you add the number to the number. Are you paying attention? Okay. You add the two numbers together. So you got a number plus a number. You add them together, you get a number. And then what do you do over here? So if you had them both at 10 to the 5th, it would be what? 10 to the 10th, right? Because you add them. No. You keep the exponent. In other words, you can think of it this way. Number of oranges plus number of oranges. They're still oranges. Does that make sense? Okay. If it was 10 to the 4th, okay, this number of apples and this number of apples, okay, they have to be the same. And then you would just leave it the same. The exponent, you add the number and leave the exponent. Okay. And that's for adding or subtracting. I guess we could do an example. Definitely should do an example. Start over. All right. So the example is 5 times 10 to the 5th plus 4. Forgive me, I'm not putting the point 0. The math still works out the same. Times 10 to the 4th. So we're adding. What are we supposed to do? Huh? You said it. We got to have the same exponent. We can't add it yet. So there's two ways you could do this. One of them you'll end up with a scientific notation. The other one will be kind of like it, but not quite. So here we go. Could I change this to make it 10 to the 5th? How would I change it? I'd need to move this to the right, to the left. So this is going to be 0.4. Okay, we just changed that up. So now once I add it, what would it be? 5.4 times 10 to the 5th. But I could also, it's equal to saying, all right, well, I want to leave 4 by 10 to the 4th the way it was. So I'd have to change 5 to a what? To 50. So it'd be 50 times 10 to the 4th. See what I did there? To make a match. So now it would be what? 54 times 10 to the 4th. Good. Now, notice I have the equal sign there. 54 times 10 to the 4th is equal to 5.4 times 10 to the 5th. Does that make sense? Yeah. Now, which one of those is in scientific notation, though? They are not both in scientific notation, because in scientific notation, the decimal place goes where? After the first non-zero digit. So we would have to have it here. Does that make this invalid? No, it's just not in scientific notation. If we wanted to put that in scientific notation, what would we do? We would convert it to this. It means the same thing. Okay, does that make sense? Is that crazy? It's crazy like in a good way, like it makes sense, hopefully. Okay. Multiply. Okay, we're going to do the exact same thing, except now we're going to multiply. Same numbers, okay, but we're going to multiply. Do I have to get the exponents to be the same? No. So here's the rule. When you multiply exponent numbers, the numbers multiply and the exponents add. Put that in your notes, or make sure it's in your noggin. When you multiply, to multiply exponential numbers, the numbers multiply and the exponents add. When you multiply the number and you add the exponents. So, right here, what's 5 times 4? 20. And times 10 to the what? 9. You add the exponents. 5 and 4 is 9. Got it? All right, so if you multiply the numbers and add the exponents when you multiply, what do you think you do when you divide? You divide the numbers and then you would what the exponents? Subtract. Good. Good. That makes sense, right? So let's go ahead, drop down. All right. So, gosh darn, 6 times 10 to the 3. Divided by 2 times 10 to the negative 5. Remember your rules from elementary school. What is 6 divided by 2? Okay, so this would be 3 times 10 to the what? Take a second, think about it. Don't blur out. Why 8? Because 3 minus a negative 5. Have you ever seen this before? 3 minus negative 5, add opposite. Okay, good. Glad you remembered that. Excellent. Can we move on? Is everybody feeling comfortable? Awesome. Challenge. Did anybody do the challenge? Sure, that doesn't sound very like, let's go. I'm not inspired. Like, did you do the challenge? Sure, I did the challenge. Did you do the challenge? Yeah, she's nodding yes. Okay. All right. Trying to catch up. Okay. Alpha Centauri. A, Alpha Centauri B, and Proxima Centauri. Maybe I'll teach you something extra beyond this. I don't know. Heads up are usually a good thing. Heads up are usually sleeping. Heads up. I might happen to accidentally teach you something. Okay. So It says that they appear to be the brightest star in the night sky together, the three of them. They're too close together for us to, with our blind eye, see them individually. Does that make sense? So it looks like one big bright star, but it's actually three. I think most commonly people call them a trinary star system. I think, and I'd have to check this, I shouldn't tell you, but you can correct me if I'm wrong later. I think A and B orbit like this around each other. Does this look like, if the point of my fingers, or these two, are those two stars, and they're orbiting like this, are they orbiting around each other? Or are they orbiting around a common center of gravity or center of mass? Okay, they're not orbiting around each other. They're orbiting around a center of mass. Does that make sense? In between them, probably not perfectly, they're not exactly the same mass, but in between them, there's a point that they're orbiting around. Does that make sense? And then I want to say Proxima Centauri B orbits the pair. Does that make sense? Let me ask you this way. Does the Earth orbit the Sun, or does the Sun orbit the Earth? The Earth orbits the Sun?
Yeah.
Okay. What if I were to tell you it'd be more accurate to say that the Sun and the Earth orbit a common center of mass? That is more accurate. However, because between the Earth and the Sun, the center of mass is within the Sun, we can, in common language, say the Earth orbits the Sun. True? Okay. I'm splitting hairs here, I know. But let me extrapolate this now. Okay? Does the Earth orbit the Moon, or does the Moon orbit the Earth?
The moon orbits the Earth.
The Moon does orbit the Earth. However, we could be more precise and say that the Earth and the Moon both orbit a common center of mass. Good. Now, let's extrapolate it out even more. Does Pluto orbit its moon, Charon, somebody said it was Chiron, I don't know. Or does that moon orbit Pluto? The moon orbits Pluto? Okay. Or would it be more precise to say they orbit a common center of mass?
Yeah.
In fact, that's the only accurate way you could say that one, because the center of mass is not inside of Pluto. This moon that's spelled C-H-A-R-O-N, I want to say, Charon, Chiron, whatever, is so massive in relation to Pluto. It's still smaller, but they're so close that their center of mass is not in Pluto. It's somewhere in between. Okay? Probably like a third of the way out from Pluto to Charon. So they're kind of like tumbling around each other, I guess. It'd be like if you took two markers, one a little more massive than the other, tied a string between them, and threw it, they'd tumble end over end, wouldn't they? Okay? The center of rotation would be the center of mass, if that makes sense. All right, cool. That's a lot of numbers, guys. I'm going to do the top one. You're going to do the bottom one. Write this out, though. Follow along. 41 trillion 200 billion kilometers. That is the distance from our sun out to both Alpha Centauri A and B. And then we have to Proxima Centauri, we have 39 trillion, was it 900? Yeah, 900 billion kilometers. It tells us that a light year, one light year, is equal to 9.5 times 10 to the 15 meters. So we have, what would we call this? We have an equality that's showing a relationship between different units, which we would call a what? It was literally like, what, 2 or 3 instructional days ago? We talked about We're converting from one unit to another. A conversion factor. This is your conversion factor. This is to go from light years to meters, or meters to light years, right? Okay, but what are we in? So what do we need to do first? Kilometers and meters? Okay, we can do that. What do I do? Times what? Oh, you said divide. Ooh. Guys, what is a kilometer?
3 miles. Or no.
Most simply, it's 1,000 meters.
Yeah.
So if a kilometer is 1,000 meters, I'm in kilometers. What do I need to add or subtract? No, not 1,000. How many zeros? Or you could look at it that way, say I need to either multiply by 1,000 or divide by 1,000. Which one do I need to do? I need to multiply because I need more meters to cover the same space than I do kilometers, because kilometers are bigger units, right? So I need to add what? How many zeros? 3 of them. 1, 2, 3. 1, 2, 3. All right. Now what? This is in what? The conversion factor is in what? It's in scientific notation. Wouldn't it be useful if we didn't have this gigantic number? Some of your calculators might not even take a number that big. Okay? So, I'm going to do the top one. You're going to do the bottom one. Okay? Ready? Scientific notation. The decimal goes just after the first non-zero digit. Okay? So it's going to go right there. I'm going to erase that. I'm going to put it over here. 4.12 times, because all these zeros are insignificant figures because there's no decimal point here. If there was a decimal point here, oh, we got to put all the zeros. Okay? We got. So 4.12 times 10 to the how many? How many do we need to move it? We'd have to go from where the imaginary decimal point is. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So 1, 2, 3, 4 times 3 is 12, 13, 14, 15, 16. I lost my place. 1, 2, 3, 4 times 3 is 12. So that'll be 12 here. 13, 14, 15, 16. Okay, 16. So times 10 to the 16. Now, if I'm going to the left, that does what? We move the decimal to the left, so this 16 needs to be what? Positive, so we leave it alone. Okay? Down here, it's your turn. Turn that approximatory distance into scientific notation. In 3, 2, 1.
3.9.
Okay. All right, enough with the whistling. It was bad enough when I did it. Now what? Now what? Good. We're in the same format. It's a conversion factor. With conversion factors, we're either going to do what type of math or what type of math? You're going to do what or what? You're either going to multiply or divide. Okay, cool. How do we figure out what we're doing here? We're trying to go from what to what? We have meters, and we're trying to go to which is bigger, a meter or a light year? By a lot. Hello. Takes a lot of meters, okay? So if we're going to a bigger unit, the number will have to get smaller. So do you think we're going to take this and multiply it? Or are we going to take this and divide it to get a smaller number? Divide. Now, unless we had some kind of crazy negative something going on, then it gets, you know what I'm saying? But it should be divide in this case. So we're going to go 4.12 times 10 to the 16 divided by, because we want to make it smaller, because a light year jumps a lot more territory per unit, by the conversion factor, dividing by the conversion factor. Do we remember the rules for dividing in scientific notation? What's the rule?
You have to subtract the exponent.
Subtract the exponents,
And this one was,
this one from this one, and then
yeah, just go in there.
and then just divide this. So with your calculator, go ahead and get it out. 4.12 divided by 9.5. You will get a number. Don't say anything yet. You've got the number, but we have to do something else, right? So what's the times what to the what going to be? Huh? Just 1, right? Times 10 to the 1, because 16 minus 15 is 1, yes? So I need to move the decimal for whatever answer you got by 1 place to the right. So you're going to answer the question in 3, 2, 1. Not 0 point. 4.34, I think we could round.
Yeah.
Okay, good. So we were at 0.433, whatever, but we moved the decimal 1 place because it was times 10 to the 1. Okay, so we have that number. What's the unit going to be? Light years. Remember, we were trying to convert to light years. We're done with the distance to Alpha Centauri, Alpha, and Bravo. So let's do the same thing for the bottom one. Same thing. You're going to plug that number in the top, put the conversion factor in the bottom, divide it out. Go ahead. I'll give you like 60 seconds or less. 3.99 times 10 to the 16 divided by 9.5 times 10 to the 15. And what'd you get? 4.2 light years. Excellent. All right, moving on. So we've calculated each star's distance from our sun in light years. And then what we can do over here is you just adjust this to be the right distance, just so you kind of see a visual of it. You guys can do that on your own if you want. And we're going to challenge me. This should be fast. 1 light year is equal to 9. You guys can do this on your own, can't you? In fact, most of this is just looking back at what we already did. Okay, so I will leave the challenge me. Was it 7 or 8 questions? 8 questions. I'll leave that to you guys. Significant figures. Rules about significant figures. Let's take a look here. All right. Can we all agree we got 1 major unit, 1 centimeter? The green is what we're measuring. Do we have 1.1? Yeah. Do we have 1.2? We can actually measure it. Can we measure to 1.3? No, we could estimate, but can we all agree that it's actually in between there? So it'd be 1.2. We already have a point. You can't have more than 1 point. Probably 1.24 or 5 from my eyes. It says it'd be 1.25 or 2.6. Okay, good. That's in proper significant figures. There'd be 3. So you have the 2 that you can actually measure, and then the last digit is going to be the one that you're estimating. Does that make sense? So here we'd have 1, and it's dead on 1. So they're saying, hey, you measured 1, and you measured 0, and then you estimated that it didn't go any further. So you still have 3 significant figures. Again, this is 3 significant figures. Okay, you count both those zeros because they're on the right-hand side of the decimal. And there's no other number to the right. All right, this one, what do we have? What do we have? 1.15 again. Okay, maybe 6. How about that one? Look like 1.5, and then we estimate no more. So 3 significant figures again. In all these examples, the measurements indicate that the measuring instrument had subdivisions of 1/10 of a centimeter and that the 100th place is estimated. So you can actually directly measure to the tenths, and then we would estimate 1 past that, and that's as far as you go with significant figures. In our system of writing measurements to show significant figures, we must distinguish between measuring zeros or measured zeros and place holding zeros. Here are the rules for determining the number of significant figures in a measurement. Okay, rule number 1, all non-zero digits are significant. Anything other than a 0, for sure, 100% of the time, is a significant figure. All zeros between non-zero digits are significant. So if you've got a 0 sandwich, they're all significant. All beginning zeros are not significant. So if the numbers to the left are zeros, you don't count those until you get to a non-zero number. We'll go over some examples. Number 4, ending zeros are significant if the decimal point is written in, but it's not significant if the decimal point is an understood decimal. Like you understand it's there, but it's not written in. So here we go. First example, 543 has 3 significant figures. 22.437 has, all of them are significant, 5. Understood? Pretty simple, right? That rule is pretty easy. Anything not a 0 is a significant digit, figure. 2, all zeros between non-zeros are significant. So 7,004, because those zeros are sandwiched between non-zero numbers, you count them all. So 4, this one, you've got zeros sandwiched, so you count all of it. So you got 6. This one, you have 3. Any questions on that? Okay. Third rule, all beginning zeros are not significant. So even if the 0 is to the right of the decimal point, if it still hasn't come in up to a regular non-zero number, then it's still not significant. So in this case, only the 7 and the 5 are significant figures. Right here, you don't count anything until you get to a non-zero. So you got just 1. This one, these 2 are not significant, but these 2 are. So you have 4. Does that make sense? Yes, no, maybe? Ending zeros are significant if the decimal point is actually written in. So 37,300 to 37.300, all of those are significant. This one's got a decimal point here, so all of it's significant. This one has 3 because it has a decimal. Same number, but there's no decimal written in, you don't count the zeros, so just 1. So if I asked you, like orally, verbally, I said, hey, how many significance does 100 have? You'd say, does it have a decimal or not? Because if it does, then it's 3. If it doesn't, then it's just 1. Okay. Addition and subtraction. To answer an addition or subtraction operation, must not have any digits further to the right than the shortest addend. So the number with the shortest, the least significant figures, your answer is going to be rounded to that decimal place. Does that make sense? So here we have 3 numbers being added together. The one with the least number of significant figures, that's the answer you're going to have as far as past the decimal. So we have 2 past the decimal here. We have to round our number to have 2 past the decimal there. Because you can only be as precise as your most precise measurement, right? Or as your least precise, excuse me. Multiplication, division. Ooh, I don't know if I remember this one. It's been a minute. An answer for a multiplication or division operation must have the same number of significant figures as the factor with the least number. Okay, so same. Same. And they've got some examples. All right, summary. This conversation that constantly goes on between you two, that's the last chance. I'm going to move you if you can't stop talking. I'm glad you all are friends, but it's the whole time. Summary, make sure this is in your head or in your notes. Mathematics is a major tool for doing physics. I mean, oh, duh. That probably doesn't need to go in your notes. The very large and very small measurements in physics make it useful to express numbers in scientific notation. That's your I can statement. There is uncertainty in all measurements. Measurement is imperfect. The use of significant figures is one way to keep track of uncertainty. That's true. Measurements must be written with a proper number of significant figures, and the results of calculations must show the proper number of significant figures, which we just read the rules to. And we have all the rules. Okay. Review. How many minutes do we have? Write the following, and we did some examples together. Do we feel good? You guys feel all right? All right. Y'all are released.